trouble.
I don't know. No more music.
Hi, I'm Professor Usaki. Before we start the lecture, there are a few things that I need your help. First, please mute your microphone most of the time unless you are asked to provide your feedbacks or questions. Second, if possible, please use a headphone or earphone instead of a speaker to receive the best voice quality of the lecture. In addition, using a headphone also helps us to avoid the echoes when you are expressing your thoughts. Finally, this is an interactive class. You may be asked to answer a few pop-up questions during the lecture. Please pay attention to what's going on right now. Thanks for your cooperation. Now, please sit back, relax, and enjoy the lecture. Good afternoon, everyone. So I'm so glad to see a lot of you are here still. I know some of you probably are still trying to figure out what's going on right now, still trying to figure out where the link is. But if you have some friend who is asking you on Piazza or whatever, because I cannot reply, but tell them, like, if there is a link in iLearn, please log in, please find out where we are. And if they cannot even log into iLearn, like they have an issue with that. So today we are going to be our second lecture. And some of you, if you joined our stream earlier, you probably already heard the song that Don't Worry, Be Happy. It's an old song, but there's a reason why I play that one is because there was a day that I walked outside and, well, because right now we are in a social distancing, stay at home device, so we cannot actually stay outside too much, but you are still allowed to walk with your dog or bike. And turns out that some of my neighbors, they have one dog, but the dog has been outside forever for the day. But that's another story. But one thing I feel really touching is that when I step outside, I saw someone use this chalk and put this "Don't worry, be happy" on the way. So we know we have a lot of issues since the coronavirus start to spread out. We know we have a lot of issues with a lot of things, even for our first lecture. But don't worry, be happy. We will get everything. We will get through everything. So so right now, let's get started. So last lecture, we were talking about what logic design is. So the very, very basic or the definition from the encyclopedia, what it tells you is that it's the organization of the circuitry of the digital computer, and we know how important digital computers are. So that's why we start to pay attention to. We start paying attention to this kind of. That's why we have to pay attention to this kind of design, the digital circuit design. And And so all digital values are based on two valued logic system, 1 and 0, on and off, yes or no. And computers perform calculations using computers called logic gates, which are made up of integrated circuits that gates pass or blocked cycle pulse, clock pulse as it travels through them. So that's that. So the rest of the stuff we are going to learn, but the most important thing that we learned in the last lecture is that it's basically a two-value logic system. So for this two-value logic system, right, how we make an input signal to become two-value, it's basically that we convert the signal, and like if you have learned physics, if you have learned basic electronics in the past, it's basically if the current comes in, it's analog, it's contiguous, and we have to quantize this into different levels, and the levels in the binary system, the basic one is zeros and ones. You can definitely make them more finer grained, but the cost is even higher in this way. So the most important takeaway here is that in digital circuit, we are going to lose some precision. We are going to lose some range of the values we cannot express. But there are another important reasons why we need to use this kind of not so perfect signal to process our data, is because the cost of building such kind of system is now lower with digital computers, because thanks for the contribution from a lot of engineers in the past. And digital signals are less fragile to noise and defective components, because thinking about the range can be distinguished as 1 or 0s. They are large, and the digital data are easy to store, because you don't have to worry too much about the environment that you store the data. Comparing with the analog storage, you still have to worry about some of them, but not all of them. So so that's the basic idea of digital signals. And and the basic so if we want to express data with such a digital system, we have to convert numbers or some kind of the original value into the stuff that the digital circuits can understand. So it turns out that you have to convert from decimal to binary, or every other number system to binary. So these are all what we have learned in the past. So right now, today, the lecture we are going to talk about, there are two types of logics that you are going to learn in this class. And we are going to start talking about one type of a logic that's called combinational logics, and what's the theory behind it. And then what's the building block of combinational logics. So these are the stuff we are going to go through today. So first, there are several different types. Well, there are two main types of circuits. And their names are combinational logic and sequential logic. So for combinational logic, the meaning is that the output of such a logic is a pure function of its current input. So no matter what time, what moment, as long as you give this logic the same input, it always gives you the same output. So this property is called idempotent. So this is combinational logic. And in contrast to that, a sequential logic means the output depends on not just the current input, but also previous inputs, and probably their history, depending on how you design. So this is the difference between combinational and sequential logic. And they can be used in different ways. So now I would like to encourage you to think what's the best scenario, why we need both of them in circuit design for 90 seconds. All right, time is up. So from what I learned from you guys right now, I can see the most popular answer is between C and D. So I would like to invite some of you, if you would like to express your idea, you can raise your hand, and I can let me know what do you guys think. Okay, so I have Fernando Gonzalez. Do you want to express your idea? Hello?
Hi. Well, from the previous class, I kind of learned that it takes kind of like a combination to choose a specific space in memory. So I was thinking maybe the combinational logic can come in like in the input space.
Yeah, so within this, right? So how many of the following can we use combinational logic? Like who are they? What do you think?
I it's hard for me to say, but I mean I'm pretty certain that mostly all of them can do that. Unless I can't really picture
most
them.
of them.
Yeah,
Okay,
most of them.
so tell me about, yeah, so what do you feel about the difference? So tell me what's the definition of combinational logic?
So combinational logic, the output is dependent on the input, and for
Sequential?
sequential, it depends on like the previous inputs as well as the inputs in the very beginning.
So for this four, how many of these do you think we need a previous input?
I'm kind of rusty, but I'm sure the adders, memory cells. I would like to think D as well.
Okay, so you don't think they? So you think both needs the previous inputs?
Yeah.
So can they use sequential? Can they use combinational logic?
I think so. I'm just really
okay,
rusty. I would have to actually see it.
Okay, so maybe I would add other people. All right, so Fan Zong Li.
Hello, can you hear me?
Yeah.
Okay, so first of all, I think I picked C.
Okay.
I think that the memory cells and the number 4, those two can be accomplished by combination.
So you think memory cells and decimal to 7 segment? Okay. So any specific reason? So what's the input of memory cell?
I think.
What's the functionality of memory cell? Tell me about that.
It's just to store. It's just to store store a digit.
Okay. So store a digit. Is it the current input or the previous input?
I think a current input, because you really don't.
But why you need to store it? Why do you need to store
it for later use? So maybe later.
For later use, right?
Yes.
So then, what does it mean? You are using this circuit to do what?
To store a digit.
To store a digit, or say to preserve the previous input, right? So is this going to be a combinational logic or a sequential logic?
But to store a digit, you don't need a previous output, do you?
Well, you use the current input, but you output the previous, right? That's memory cell. Right. Okay. The input is the input you fit in, but the output is affected by your previous storage, right? So if originally here there is a 1, then the next cycle, when I try to output this memory cell, it gives you 1, right? And it's depending on the previous input, not your current input.
Yes, it's a latch, right? Yes.
Right.
Okay. Yeah, I see.
So then in this way, which one do you think? Or what are the ones that you think we can use combinational logic?
I think, can you explain number 4? a little bit more.
So decimal to 7 segment, you guys know what a segment is, right? So
I
like
don't.
LED, right? You must solve this kind of expression, you know, it's 3, right? And like if it's 8, it will use all the 1, 2, 3, 4, 5, 6, 7 segment to express the number.
Okay.
So that's called 7 segment LED decoder. So do you think this one would need any memory?
I don't think that one needs previous output.
Okay, so this one, do you think it can use combinational logic?
Yeah.
Okay, so we know this one can use combinational logic. Okay, all right. So Michael, well, Michael, do you mind to Michael Liu? So what do you think? What do you think? Hello.
Oh, actually, I was just saying I did misunderstand what number 4 meant. I thought it was talking about like sequential data in.
Okay, so what do you think now?
In terms of what does combinational logic, the other thing would be the adder.
The adder. Why?
Yeah. Because adders add things. They don't have memory. Just combinational logic, no memory. Sequential logic, memory.
Okay, awesome. All right, so I think Michael gave us a pretty good comment on that. So everything that requires previous history, everything that requires previous memory, previous input, or its output is depending on the previous input, we cannot use simply combinational logic to accomplish, right? So so if you look at all these 4 options we have, if we look at all these 4 options we have for the okay, so for the counters, right, you need a previous input, because how do I know what's the next cycle I have to output? It depends on what was the previous value in there. If the previous value even though the input is always 1, because for the counters we add up 1 every time, right? Even though the previous input is always 1, but depends on what's the new value inside. For example, if your new value, the value inside the counter, for example, if your value is 2, then the output will be 3 the next cycle, right? However, if you have a 4, then the next cycle will be 5. So the output need the previous input, depends on the previous input. And for the adders, if you want to do like 1 plus 2, it should always be 3, no matter what's the next equation you evaluated. And for memory cells, again, you need to keep the current state to output for the next cycle, right? So if the last cycle give you a different number, then you have to output a different number in the last cycle. And for the decimal to 7 segment LED decoders, if I want you to show up a 3 using the LED, it should always give you the same shape, right? So then, so how many of the following can use combinational logic? Actually, the answer would be 2, not E. All right. So thanks a lot, and I hope you understand the key difference between combinational logics and sequential logic in terms of the engineering meanings perspective. So in terms of engineers, all we need to know is that combinational logic is something that you need idempotent behavior. So every time you feed the same input, it gives you the same thing, like an NPC in the online game, right? If you click the NPC, it always gives you the same behavior, right? However, for sequential logic, it's not like that. It has memory. So so that's the engineering perspective. However, from the theory guys' perspective, they have a different ways of seeing it. So the combinational logic is the implementation of Boolean algebra function with only Boolean variables as their inputs. And sequential logic is the implementation of a finite state machine. So if you come from a computer science background, you probably already learned Boolean algebra in your discrete math and finite state machine from your computation theory class. All right, so that's the So, but we people from diverse backgrounds, so we still have to go through this Boolean algebra, which, being honest to you, I hate them the most when I am a sophomore. So, but unfortunately, because that's the theory that we have to use, so it's better to understand it. So right now, let's take a look at the basic idea of Boolean algebra and the history of it. So there are several different. So depending on who you are talking about, right? So if you are talking about Boolean algebra with me, then I will tell you this is the Boolean algebra. It's introduced. It's the algebra that only has two values, 0 and 1s, available in the number system, and it introduced three fundamental logic operations and or not, and that's a Boolean algebra that all of us know from the engineer's perspective, and it's first invented by George Boole, so that's why it's called Boolean algebra. However, if you talk to a mathematician, he will tell you, you don't understand what a Boolean algebra is. He will tell you that's not Boolean algebra, because from a mathematician's perspective, a Boolean algebra can be used with set operations like intersect, union, complement, and they have a set tree or whatever, and they have a set theory to describe a Boolean algebra, and it could be overly complex from my perspective. So that's their perspective of Boolean algebra. So depending on who you are talking about, and the mathematician will tell you, the Boolean algebra you guys are mentioning is actually the second, switching algebra. That is invented by Claude Shannon. So he wrote his thesis demonstrating that electrical applications of Boolean algebra could construct any logic numerical relationship. And when he talked about switching algebra, he know that, well, for engineers, we don't need this set theory. We don't need this abstraction that mathematician really likes. So we're casting the switching algebra to only have the two element, to be just the two element Boolean algebra, which we just mentioned. You only have two Boolean variables, and it's not something that complex, right? And but now, if you so that's the mathematical definition of Boolean algebra, is that it's actually switching algebra, and we are now using switching algebra and Boolean algebra interchangeably in EE. But if you are interacting with a mathematician, saying like you're a math professor, okay, don't say this is the Boolean algebra. We are actually using switching algebra. So depending on who you are talking with, if you are talking with Professor Usaki, you say, well, this is Boolean algebra, I will give you full credits. However, if you try to answer this to your discrete math professor or any math professor, don't do that. All right, so that's the basic definition of Boolean algebra. And here are more concepts about the Boolean algebra. So the only two values that are available in their inputs outputs are 0s and 1s, and they have basic operators like and, or, and not. And definitely you can use a truth, but here's the basic concept I want to give you regarding the definition of each different operators. So for AND operator, you can imagine it's an operator that returns 1 only if both inputs are 1s. And otherwise, it always returns 0. And OR is the operator that returns 1 if any of them is a 1, and returns 0 if none of them are 1s. And NOT is an operator that gives you the opposite value of its input. So remember this. This is a very basic thing that you should memorize. So if you can also express the same idea with another thing called truth table. So the truth table, it gives you a table that sets out the functional values of logical expression on each of their functional arguments. That is, if you give it lists all the possible inputs and their all possible outputs. So that's the truth table. So for the truth table, as you can see, right? For and, if I give you an input like 0, 0, because both of them are 0, the output is definitely 0. And for if I give both of them to be 1, then the output is definitely 1. However, if some of them are zeros, then the output would definitely be 0, because the requirement of AND is that it only output once when both inputs are ones. And for OR, it output once whenever any of them is a 1. Only output 0 when both of them are 0. And for not, it just gives you the flip. All right. So right now, I believe, given this very slow movement of what they are, you should remember their definition. So what I really wanted to do is that why don't you spend 90 seconds to let me know what are the outputs of these guys for the above function. All right, so I see 76% of you have answered. So if you haven't answered, sending your answer within 5 seconds. 5, 4, 3, 2, 1. Okay, so time is up. And right now on your screen, you should be able to see most of you pick the answer as C. But how do you guys know what are the two that you guys think that that are right? So that would lead an output of 1. So can some of you tell us what do you think? Okay, so Sahas, hello.
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 So
Yeah.
I thought that the in order to get an output of 1, the two options would be 3 and 4.
Okay. Why 3 and 4? Can you go through that with us?
So if the So if we have x at 1 and y at 0, then the x and y would result in a 0 because 1 and 0 would give you 0. And then if you do 0 or x, which is x is set to 1, that would result in a 1 because 0 or 1 would give you 1.
Okay, so it's like the table, right?
Yeah.
So if you look at the table, then you will figure out that, well, like, yeah, as you said, right? If I give input both as zeros, then y prime will be 1 and xy will be 0 and xy or y, x will be, the result will be 0, right? So this is how you get the last two output as the right answer, right? Okay. So I guess we should be good with this question. If so let me put all of your hands down. If you still don't understand, raise your hand again. Okay, so I got Kevin. Okay, Kevin, how can I help you?
I don't really need help. I was just lowering my hand myself before you did it for me.
Okay, awesome. All right. So I think we are good with this question. So and I think through this analysis, you know, the most important, you have the basic idea of what a Boolean logic. Well, how come I always pick the answer as E? So the answer should be C, right? So this is the answer for this question. Okay, so let's go advance. You guys know and or not. However, there are more. So for example, people derive other operators like NAND, NOR, and exclusive OR and exclusive NOR. So in circuit design or in Boolean algebra, they are useful in some ways because they can help us to express your Boolean functions or your circuit in a more distinct way, right? So let's look at the definition of them. So for NAND, it's basically not AND. So it's having the not result of your end result. So if you remember, the previous output for AND is for this set of values is basically 0, 0, 0, 1. And for the output of not NAND is basically the flip of it. And the same thing for NOR. If you remember what an OR is basically 0, 1, 1, but right now with NOR, it's the flip of it. And the other thing, which we kind of like mentioned in the first lecture, the Boolean operator exclusive OR. The exclusive OR, if you look at the Boolean definition, is very complex. But what I want to tell you is that exclusive OR is something if both inputs are the same, we will give it a 0. So for 0, 0, because both inputs, they are the same. So we had a 0. For 1, 1, because both inputs are the same. So we give it 1. And for those are different, then we will give it 1. So that's the meaning of exclusive OR. So if we want to tell two numbers if they are the same or not, just do an exclusive OR. And if you see a number that in your left-hand side appears on the as the right-hand side, if they are the same or some of the bits, they turns out to be the same, then this bits they show up together would gives you a 0. So if you are given a set of number and if each number shows up twice, and if you exclusive OR all of them together, then turns out you will get 0 because each of them show up twice. When you have another number appears again, they will cancel out those ones in your result. So these are the reason why for the LeetCode question that I showed in the very beginning of the class, the answer is using exclusive OR. So I see, Michael, you have a question. Hi, how can I help you?
Oh, actually, I wanted to make a comment
Okay.
about exclusive OR. If some people are having trouble with it, the exclusive OR operation can also be understood as the bit flip operator, in which the bit on the left-hand side is flipped if the bit on the right-hand side is 1, and it is left alone if it's 0. It's understood this way because it's often used this way in what you will see with how checksums work.
Okay, thanks a lot. All right, so okay, I also have Fernando. Fernando, do you have any question?
Well, I just wanted to comment. To be honest, I kind of was left a little more confused with what we just said. But I'm pretty sure we'll at some point run into this, right?
Yep. Although not in the rest of this lecture. So if you want to figure out what exclusive OR is, this is the best time. So what I want to say is that exclusive OR is something that if both of your inputs are, it's really useful if you want to compare the difference or how different two inputs are, right? And if there's no difference, it will give you zeros. Okay, would that be clear? All right, so let's go ahead and keep going on. So and another one is called exclusive NOR. So exclusive NOR is actually the NOT of exclusive OR. So as you can see, for exclusive OR, whenever the output is 0, right now becomes a 1. So its function is actually similar to exclusive OR, but being represented in a different way. Okay, so these are the basic theory. I want to say it's theory, means that it's not how we are going to do it. So right now I'm going to tell you how we are going to do it. So how we express Boolean operator functions in circuit gates. So here are the symbols of Boolean operators and their circuit gate representation. So, and you have to memorize it. You have to memorize it throughout the whole class. And this is also the same symbol being used on your Zybook. So this one is the AND, this one is the OR, this one is the NOT. And for the NOT, the representation, sometimes we just take this part. So if you see, so for example, if I put a circle right here, it means that saying that if I have an input of A and another input of B, saying that what I'm using this is actually not A and B, instead of using the pure A as the inputs. So people usually doing this kind of convention in a way that, well, if I have a not get on my input, I just put a circle here. The same thing, if I have an output as a not, then I will put a circle right here. So that's why if you look at if I have an out, so if you look at what a NAND is, it's actually pretty much the same with AND, except for there is a circle on its output side. And for OR, and for OR, I have NOR as well. And how to do a NOR is how to represent a NOR is just put a circle on the opposite side of the OR. And for exclusive OR, this is what it looks like. And as you can tell, the not exclusive OR is exclusive not OR. then exclusive NOR is actually putting a circle on the output side, right? So this is the representation of their circuit gate symbols. So right now let's have more right now let's use this circuit gates to see how a Boolean function can be represented with circuits. So right now saying that I have y equal to E and A and B plus, or say, or C and B and D, right? So this is the Boolean equation that I'm going to make them a circuit. And for this function, the output is the y. So what I will do is that I will have to put a y here, and then another input I have is E, right? And you know I'm going to have E and something, right? You have E and something, right? So what's that something is actually A, B, or C, D. So you know to get the OR, you need an OR gate. So you put an OR gate here, and where are the left hands? Who are the left hand side and the right hand side of the OR? Is actually two ends. One end is AB, the other end is CD. So let's just keep going. This is the AB, this is the CD. Here we go. This is the circuit with gates representing Y equal to E and A and B or C and D. So that's how you can express the Boolean function in a more engineering way. All right. So that's the idea, right? And if you look at this circuit, I'm going to have more evaluation of a circuit. So to express this simple function, right? It looks pretty simple. However, it would take us 5 inputs, A, B, C, D, E, 1 output, Y, and how many gates? A total of 4. And how many wires? Or it's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Total number of 9 wires, or say signal nets. That's the circuit, right? So if I want to express this function, it actually took me 5 inputs, 1 output, 4 gates, and signal nets. And how many pins? Because remember, for each gate, I have to connect with the wires to get my input and put my output. So for N gate, I have 2 inputs, 1 output, so I need 3 pins. So I have, and for all gates, I also need 3 input, 2 input, 1 output. So I also need 3 pins. So I have a total of 4 gates, and each of the gates will require 3 pins. So it turns out I need a total of 12 pins to implement this circuit. So this is one way. This is one way we are talking about how we can express the function. However, in circuit design, usually we don't use and or not. Instead, we try to use universal gates like NAND. So NAND and NOR, they are so-called universal gates because we can use these 2 types of gates to express any other logic gates. So for example, if you want to express what an AND is, it's actually an AND, a NAND, and connected by another NAND, but both inputs are the output of the previous gate, NAND gate. That's an AND. If you want to express an OR, it's using both inputs as using both inputs as the inputs of different NAND gates, and use that output to connect with another NAND. That's an OR. You can also use a NAND to represent NOT in this way. So if you know this is NOT using NAND, then this is NAND plus NAND and NOT. So that's how you get an AND, right? So that becomes easier to understand. So right now, I think you buy the idea that if you want to try more, you can use Boolean algebra to derive, and you will know they are all equivalent. The circuit gates that I draw here, they are all equivalent. And the same thing, you can also make everything NOR. So if the original circuit is taking an AND, and the OR, the NOR is like the NOR representation is like this. And if the whole thing is an OR, then it's actually like this. And if it's a NOT, it's like this. Okay, so I have Fernando. Question?
Yeah. So after, I just want to ask this question. Is this really cheaper? We're using a lot more components and it seems really complicated.
Okay, I will have an answer later on. Okay, just hold on a little bit. Okay. So this is how we express y in the very beginning, right? You remember that. And if I want to use everything as a NAND, as Fernando just mentioned, right? I'm using more gates. But why am I doing this? Why am I doing this? So let me show you, let me explain this a little bit, and let me explain more about this. So it turns out it's a relationship with how these gates are implemented. So well, you guys know that I have a computer science background, but not an E background. So I'm actually not an expert telling you the physics side, why there are simply two types of MOSes and what's going on within this CMOS when you do something. But only you need to know, and well, so the thing is that I survived, and I work at Intel, the biggest microprocessor company in the past, and I'm fine. I survived. And my friend who is currently working in Qualcomm, he doesn't. When I ask him about, oh, do you remember what is NMOS, what is PMOS? He doesn't even remember, and we survive, right? So it's not really important to dig into the detail why NMOS or PMOS behave like this way, but this is what you all need to do is that there are two types of CMOS, and we use them to build gates. And here are the two types of CMOS. So for NMOS, right, it turns on. So each MOS, you have three different inputs. So you have the gate, you have the source, and you have the drain. And when you put the drain, when you put the value of 1 to the gate, then it will pass zeros, but it will not pass ones. So this is the meaning of it will pass zeros here, right? So this is the definition of NMOS, right? And so this is called sorry. The output should go this way. right? And so you connect, well, sorry, okay, I'll explain that later, right? But the thing is that the output of the gate would be zeros, right? And for PMOS, it's behave in a different way. If your gate is passing a 0 value in it, then I would pass ones as my output. So the thing is that if you enable NMOS, meaning that you give it an input like 1, then it gives you a 0 as the output. This is called pull down, because I give you a value of 1, but you make it 0. And for PMOS, it's behave in a different way. If I give you a 0, it would output 1. So it's called pull up network, because my original value is 0 and it lift it up to 1. So that's the definition of these two types of MOS. So if I want to use this two to build a gate, so for example, like NOT gate, right? What a NOT gate really needs to do is that if I have an input of 0, then I want the input to be lifted up as a 1. So I need to make the PMOS on, right? So turns out that what you need to do is that you put the input directly to their gate, and turns out that and this part is the PMOS, this part is the NMOS. And for the PMOS, because whenever you put a 0, it would lift it up. So the output turns out to be 1. And for when you are going to have a 0, when you are going to have an input as 1, because we will need to pull it down. So whenever the gate is 1, it goes to the NMOS, and it would give you a 0 as the output. So that's how we make the NOT gate. And the same theory, if you want to use it, if you want to build an AND gate, it looks like this. It will need 6 different transistors to build an AND gate. And this is what it looks like for an OR gate. It will also need 6 transistors. And right now, let's take a look of our universal gate, NAND gate. The NAND gate only takes 4 transistors to build. Only takes 4 transistors to build. And it would need 2 NMOS, 2 PMOS. And for the previous ones, you would either need 4 PMOS plus 2 NMOS, or 4 NMOS plus 2 PMOS. So that's the difference, right? So right now you see, for each AND gate or gate, I would need a total of 6 transistors, but for NAND, I only need 4. So let's look at this. Why we should be using NAND most of the time? Because NAND ORs are universal gate. You can use them to build everything. And if you can build everything with just one thing, it simplifies the design, because all we need to do is that we just put NAND gate everywhere, and your algorithm is only need a NAND gate to synthesize your circuit. And we do the same for your Xilinx software as well. So when you put a Verilog inside, it will synthesize everything into the NAND gates at the very end. And if you learn more about the FPGA, you will figure out that FPGA is basically an array of NAND gates, and we rewire those signals to their different AND gates. So and the other thing is that for NAND gates, it only makes 4 transistors. So the gate delay is smaller than those gates that would need 6 transistors. So NAND, and people prefer use NAND a little bit more, and this is the reason, because there is a slight timing difference between NAND and NOR, depending on because of the physics nature. So Oh, NAND and NOR, first of all, they are both faster than those ones need 6 transistors. However, NAND is slightly faster. So in modern circuit design, we tend to make everything NAND instead of everything NOR, even though they can build exactly the same thing. They would consume exactly the same amount of gates to build the same thing. Well, sorry, not exactly the same amount of circuit to build the same thing, but we prefer NAND because it's slightly more faster. Okay, so that's the reason why we are using NAND. So now, how about the total number of transistors? So we say each of this would take 6. Each of this would take 4, right? But if you keep going on, right, 4 gates, each 6 transistors, total 24. 9 gates, each 4 transistors, it's a total of 36. Hey, professor, you lied to me. It's not saving the cost, all right? But if you dig into the detail, right? Remember, this is a knot. This is a knot, right? If we have 2 knots, like in what we would do in mathematics is that if you have 2 negative numbers, and if you times them together, they would give you a positive number, right? So inverter is like a negative sign in your Boolean algebra. And if you have 2 negative, it gives you a positive. So if you have 2 negative, it turns out that it's canceling each, all right? Same thing here, you are canceling each. So we can just simply make them a wire. Take these 2 gates off. So right now, we only need 5 gates and 4 transistors each. We only need 20 transistors. And remember what we have. If you use and not or, is that you need a total of 24. All right, so that's another thing. It's not that trivial that you can see directly. However, if you have some algorithm to optimize your circuit, you will figure out. You will figure out. All right. So that's the question that Fernando is interesting. So anyone else, do you have question on this one? Okay, if not, I think we are going to proceed. So right now, I'm asking you this question. So we can, so far we have learned, if we want to express a circuit, we can either use a truth table or a Boolean algebra. However, if I want to express this guy with truth table, how big the table is? All right, I will give you 15 seconds. And I'm going to close the poll in 5, 4, 3, 2, 1. Time is up. Okay, so this is what I have with you. So 60% of you think it's D, and the rest of you think it's either A, B, or C. All right. So I need someone to explain why. Can you, if someone is willing to share what you think, why don't you raise your hand? Okay, I have Kevin. Kevin?
Okay, so I chose D because we need to have 32 rows, as we have 5 variables, each of which
We
can
have
have an
5
answer of
variables.
0 or 1, which
Right.
can be represented as 5 bits. 2 to the 5th would be 32.
Okay, so you got it right. Thank you. So so for this question, right? If because we have 5 inputs, and each inputs could be either 0 or 1. So each of the input, they have 2 possible values, and you have, for the truth table, you have to go through all possible values and list them all. So it turns out that you need 32 rows, and each row would have 6 columns because you have 5 inputs and 1 output. So you need 32 rows. But 32 rows is a very big table, right? So Boolean expression, as you can see, we only need this. So that's why, well, sometimes people saying that, well, why do I need to learn Boolean algebra? Because Boolean expression is a lot more compact than a truth table to express one thing. So that's the power of mathematics, right? So, but right now, let's do another thing, right? So if today you are given a Boolean equation, Boolean function, can you convert it from
2 to the 5.
the truth table, right? Can you convert it from a truth table, right? Okay, so we need to know. Okay, so Fernando. Okay, so now we have to need. So before we start this, right? We need more definition. We have to go into some more hardcore game on the Boolean functions. So here are the definition of some important Boolean function expressions. So first of all, when I say I want to take a complement of an input, or you can treat it as a not of an input, it's basically an A not, or you can some of the textbook, they will do an A bar, right? So that's the different, that's how we express not or complement in Boolean expression. And in Boolean expression, literal is basically saying a variable or its complement. So this is so A itself is a literal, A not is also literal. And implicate is the product of literals. So A, B, C, or say A and B and C is an implicate. AC is an implicate. However, if I only put B, it's a literal. Implicate, it's the sum of literals. So A or B or C, that's implicate. Min term is an AND term that includes all input variables. So if I have 3 variables and I have A, B, C, A not B, or A not B and C, because I have A, B, C all in my term as using AND. This is a min term. However, if I only have a term like A, B, it's just an implicate, but not a min term. So that's the difference. So min term is a subset of implicate that contains all input values for this function. And max term is the implicate that has all input variables in it. So for example, if I have 3 inputs in my Boolean function, A or B or C, that's the next term. A naught or B or C, that's the next term. A naught or B naught or C, that's the next term. However, if I only have A, C, or B or C, it's an implicate, not a next term. So here are the definition we are going to use for the rest of the discussion for our Boolean function. So how do I get a Boolean function from a truth table? So this is how we do it, right? So let's look at the table on the top. The term that I encourage us to use in this class is actually the sum of minterms. So for the sum of minterms, here's how we do it. Consider that you only need to consider those ones with their output as ones. So for example, the first set of input I have with output as 1 is actually when x equal to 1, y equal to 0, I get an output of 1. So what you will do here is that in your Boolean function, you put x, because when x value is 1, it gives you an output of 1, right? And you put y not, because when y value is 0, if you not 0, then it would give you 1. So you need a not y to give you the output as 1 after ending with an x. So this term could be a 1, right? And so this is a minterm because we have all the inputs from a Boolean function, right? So another row that we have, the output as 1, is actually the last row. The last row is x equal to 1, y equal to 1. Because when they are both equal to 1, we will get an output to 1. So you put an input x, y here. What it means that is that if both of them are 1, here will give you an output as 1, right? And because these are all the cases that will give you an output of 1. So this is what a Boolean function, the Boolean function for this truth table. Okay, so let's have one more iteration. So this is exclusive NOR. So for exclusive NOR, here is the truth table. And as you can see, there are 2 rows with 1s. And for this one, because we need the A to be 0 and B to be 0 to get a 1. So here it is A naught, and here it is B naught. So the first term I'm putting here, this is A naught, B naught. Another case we can get a 1 is when both of them are 1s. So this is A naught, B naught plus AB to get f of AB. All right. So this is how we get the Boolean equation for exclusive NOR from its truth table, right? And if you look at the previous definition that I gave you on exclusive NOR, let's see where they are. Exclusive NOR. Okay, the exclusive NOR right here, as you can see, it's AB plus A naught B naught. And it's exactly the same as what we just derived from the Boolean expression that I show you. All right, so this is how we can convert we can convert from a truth table to the Boolean function. All right, so far, any of you have questions? Okay, I have Chi. Hello? Hello?
Hello, can you hear me?
Yeah.
Okay, I have a question about this one. So, are we only need to consider when the output is 1?
That is true.
Oh, okay, okay, thank you.
Yep. Questions? Okay, so I have Fernando.
Hey, does this also mean that the answer to the previous question that we had is not 32? Because it could be represented
No,
with
the
less than 32, right?
well, so the last question, if you read the description carefully, right? This is what I'm asking about. How many rows do we need to express the circuit represented by this function if I'm using a truth table?
And we can
right?
use less than 32 to represent it, right? Because we only care
No,
about
because
the
you
ones.
have to, no, because, well,
Okay.
that's because when we form the Boolean functions, we only care about the ones. However, when you list the truth table, you have to tell people exactly if it's 0 and 1s.
Okay, so it has to be more explicit. We can't just simplify
Yep.
it into a simplified table.
Yep.
Oh,
Yep.
okay.
Okay. Okay, so other questions? Okay, if not, then I would have, before we end the lecture, there are a few things that I have to announce, and I have a few words to share with you. So first of all, I know we have gone through quite a few chaos of the first lecture, and in the very beginning, I thought our student can be so so first of all, thanks a lot for a lot of you email encouraging me or share me what you think about the tips. And the truth is that we know this, and we choose to not doing this for the first lecture because we want to reduce the overhead of everyone. But turns out that it's not really as good as what I was imagining. So turns out right now we have to create many links, and you have to register yourself to each of the links to get to the right place. So here is where you can find those links. So iLearn is the best place for you to find all of them. So you log into the iLearn, and you can find for the Zoom online lecture. And I didn't say that you have to do that in this lecture, because if you can see this lecture, you already did. And the links to the lab session. And if your lab session is on Wednesday, there is a link. If your lab session is on Friday, there is a link. And I believe our TAs already sent you guys the link that you should register. And there's we have a load balancing mechanism for that. So don't register to other sessions. And for office hour, all three of us, including the TA, including myself, we will be using the same link. So just register with this link. And the thing is that you have to register 3 links, one for lecture, one for the lab session, another for office hour. All right, I have a few of you have questions. So Michael, what's your question about?
Not quite a question. I just wanted to say, I know you guys were wondering how the links kept getting out. This is actually just a consequence of the fact that Zoom uses your web browser. Some people's web browsers have add-ons installed that basically scan all the websites they go to, package that data, and like ship it off. And then there are like there's like dark web companies that will take this data, run anyone's query for a price, and that's how these people get their hands on all of these Zoom invite links, because they could literally pay some money to some shady guy on the internet to get links to active meetings and then go and harass them with the password and everything. So,
okay, so
it's not, don't like try to track down any student, like, because you don't know that this is happening. It's just they scan it off the links you click.
Okay, so but on the other hand, it also means that some of us has to check out our web browser plugin, and if they think sketchy, you should uninstall them, right?
Yes, I'll always check what's running on your web browser.
Okay, thanks for your comment. Okay, I have Giovanni.
Hello. I was wondering if the labs. I heard I have another class with that labs, and they're going to start on the 3rd week. Are we starting next week or this week?
No, it's already started.
Okay.
yeah,
Thank you.
check our schedule. It's already started, and join the lab session as soon as you can. All right.
Okay.
Okay, I have approve question.
Hi. So I have a lab section tomorrow, and I was wondering
The
if
TA already
there'd be.
sent out the link, and if you already, you can find the link on the iLearn.
Okay. I'm talking
Yeah, it's
about.
already here, right? Yeah.
Right.
Okay.
I'm talking about the the software that we need for the class or for the lab.
If you can download it, you have to get it ready before the lab session. And okay, another thing that I want to be clear about the lab session is that you don't have to attend those sessions if you don't have question. We already have the video online. You can find the link through the course website, follow the link, and we also have the instructions how to do this, right? And you should follow the link, follow the manual, follow the video, try to do it again. You only need those lab sessions when you cannot finish. Okay? Is that clear?
Yeah.
Okay. So other questions? Okay, so if not, then there are a few things that I want to let you, there are also a few things that I want to let you know. So first of all, reading quiz 2 will be up to 9 and use iLearn reading quizzes. And lab 1 due April the 7th, and make sure that you know where to submit them. Other than that, enjoy the rest of your day, and I believe I will see you